Hi, everyone, and welcome to another Flan Chat. Today we have Mark Rofin with us. He is a master's student at Salland University, and his supervisor is Michael Hahn, where he's also working as a research assistant. And today he's going to present to us his work on why why are sensitive functions hard for transformers. You can take it from here, Mark.
Yeah, thank you. Today I'll talk about our paper with Michael, and here Michael was more responsible for the theory, but I'll present. But Michael's also here, so you can ask questions to both of us. So what is the problem that we explore in the paper is the following. So most works discussed in the seminar before they are about the topic what transformers can express theoretically, like what functions we can hard code in the transformers so that they can compute them. But empirically, the functions that transformers can really learn is a little bit different set of functions. So there is quite a lot of things that transformers should be able to express and learn, but they are not. So for example, there's the function parity, which we'll discuss in detail later. And there are transformers that can compute it, but in reality, it's very hard for them to learn this function if you just present them with a training set. And this is exactly what we're trying to understand in this paper, what's wrong with all those functions that transformers cannot learn. Here we explain that for highly sensitive functions, we can come up with theoretical justification why, despite them being in general capabilities of transformers, why it's hard to learn them. So yeah, this is the main goal of the paper, to explain why this happens. TLDR is that the existence theory can explain which functions can be explained expressed by transformers, but there is little theory about what they can in practice learn. And we say that sensitivity influences the loss landscape of transformers. This is related to this problem of learnability. And in principle, the more sensitive the function is, the more brittle is the minimum for a transformer that is trying to learn this function, which explains quite a lot of different scattered empirical results on the topic. I'll start the talk about explaining what sensitivity is in general. So most probably everyone knows, but still I'll briefly explain what this is. So sensitivity is a property of Boolean functions. Let's say that you have a bit string of length n, which is this x, and we have f, a function which translates x into real space. And then the input sensitivity is just how much the function changes if you change individual bits in the input. So we have x, we have f of x, and then we flip every bit in x from -1 to 1 or vice versa, see how what was the change in the output, and then the input sensitivity of function f on input x is the sum of all changes. And then average sensitivity is just the average value of this over all inputs of length n. And then the intention, how you can think about this is very simple. So average sensitivity represents the average number of bits that can flip the label. Several examples are, we can look at two different functions. For example, one parent function is first, which is just the first bit of the input. So we have x is a bit string like 1, 0, 0, and so on. And then the output is 1 because the first bit is 1. Or if the input string is different and the first bit is 0, then the output is also 0. And the sensitivity of this function is 1 because just one bit, the first one, can flip the label. All other bits don't influence anything. And another function, which is on the other side of sensitivity spectrum, is parity, which has sensitivity n. So parity is the XOR of all bits, or you can say that if the number of ones in the string is odd, then the parity of the string is 1. If the number of ones in the string is even, then the parity is 0. So for the first string here, there are two ones, so the output is 0, and for the second one, the output is 1. Here, every bit influences the outcome of the function, because if you flip any bit, then you increase or decrease the number of ones by 1, and so you change the evenness of the number, so you change the evenness of the string, and the parity also changes. That's why parity is the most sensitive function of all possible with sensitivity n. Yeah, and with these two functions, there is a little bit peculiar situation with the current theory, because parity, as already said before, can be represented by a transformer and can be expressed in RASP and in other formalisms that construct transformers. So parity should be learned by transformer, but in practice, if you have the length, the string length around 100 or even lower, but some small reasonable numbers, then transformers have really hard time learning this function. So they just don't converge and converge to outputs in constant or something like this. So this is this contradiction between theory of expressivity and practice. And with first, there is an opposite situation. So theoretically, there is a known limitation that changing the first bit in the input of a transformer can lead to the change in the output of at most 1 over n. And this influences any function like parity or first. So theoretically, if parity is hard for a transformer, then first should also be hard for a transformer because of this restriction. But in practice, first can easily be learned by transformers. So if for parity, we say that parity can be expressed, but for some reason transformers in practice do not tend to learn this function. For first, we also know, yeah. Okay. For first, we also know that it can be expressed, but for first, we can think that it has the same fundamental problems as parity. And so if parity cannot be learned, then first should also be hard to be learned, but first is easy to learn. And so that's the problem that we're trying to explain why it arises. And what distinguishes first from parity? The very simple answer is, again, their sensitivity. So first has very low sensitivity, so just 1, and first is easy to learn, while parity has high sensitivity, and parity is hard to learn. Then you can say that, okay, transformers just learn the functions of low sensitivity easier than the functions of high sensitivity. And that's indeed true because of this known, again, low sensitivity bias. And low sensitivity bias is the fact that if you randomly initialize a transformer, then it will represent a low sensitivity function with high probability. And this is not the same for RNNs, for example. So if you randomly initialize an RNN, its sensitivity will be on average higher than sensitivity of a transformer. And also, if transformer is trained for some task, it will also represent on average lower sensitivity function. So this is a low sensitivity bias, which is known empirically and described in several papers, but there was no theoretical explanation why this low sensitivity bias arises. And understanding of this theoretical explanation is the objective of the paper. So yeah, if you have any questions at any moment, please feel free to interrupt me. If not, I will proceed to the idea of the proof. Okay, so there was a paper from Michael 4 years ago that said this theoretical limitation of self-attention, which is that the inputs given to a transformer differing by 1 bit, the output of the transformer on inputs differing by 1 bit is bounded as O of 1 over n. So we have those two strings with a lot of ones and zeros. And if those two strings differ in just one position, then after transformer, the output for the first string will be some constant c. For the other string, the output will be c plus some small number, which is proportional to 1 over n. That's because the attention gets diluted on all the positions. And so in the end, change in only one position can influence, or like gets, because of the dilution of the attention, it gets multiplied with 1 over n. So this means that even if a transformer can represent, say, parity or any other function, then for sensitive functions, its output will be concentrated around 0.5. Because let's say that we have a transformer that represents parity and represents parity correctly. Then we can have two similar inputs that differ in 1 bit, and those two inputs will have different labels. So for the first input, transformer has to output something larger than 0.5, and for the second input, something smaller than 0.5. But the outputs, because of this limitation, has to be close to each other. So in practice, for long inputs, there will be something like 0.51 and 0.49. And this means that for longer and longer inputs, the outputs will concentrate around this around one constant, and the loss of such a transformer will converge to the loss of a constant with increase of input length, which is of course not what we want from transformers. And yeah, David Kang and Peter Cholok proved that if you include layer normalization with small epsilon, then we can overcome this limitation. So we can construct a transformer that does have 0 loss on a test set of parity because of this layer norm. So what happens? Without layer norm, we had that limitation with outputs too close to each other. With layer norm, this is what happens. We have two representations, say x and x prime, and they're close to each other. Then we input them in layer norm, and first in layer norm they get centered, they're still close to each other, but then they get standardized. And during standardization, each hidden representation is divided with its standard deviation. But if the standard deviation is very low and epsilon is very low, then the denominator is close to 0, and dividing with something close to 0 can very much inflate the norm of the hidden representations, which means that they can be multiplied with the value proportional to n in this standardization, which means that in the end, their difference, which was 1 over n, will become just O of 1, which is fine. So this is how layer norm with low epsilon can overcome this limitation. And the basic idea for the proof that all sensitive functions are hard is to say that this is true not only for parity, so Chang and Cholo created this construction just for parity, but this multiplication with a large value, it needs to appear in layer norm for any sensitive transformer. So not only for parity, but for any function with high sensitivity, because for any function with high sensitivity, you have this problem of the outputs being too close to each other, and you need to somehow make them far from each other, and you make them far from each other via multiplying them with large value in layer norm. But to have this multiplication in layer norm, you need, as I said, to be standard deviation to be too small. And when standard deviation is very small, this is very unstable with respect to parameter changes. Because your standard deviation depends, standard deviation of the hidden representation depends on some layers that were before computing this hidden representation. And if you somehow change the weights of those layers, then your x here will change. And with high probability, it will make the standard deviation higher. So for example, you add noise to the weights of MLP before computing this x, And now, because of this change in noise, the algorithm how you compute x changed. So the first dimension of this x became a bit larger, and then standard deviation is not close to zero anymore. Now you don't have this close to zero denominator, and you don't have multiplication with something proportional to n in layer norm anymore. So yeah, the basic idea is to prove that this this multiplication with value proportional to n is unstable with respect to parameter changes, and this is the same as saying that the minimum of sensitive transformer is brittle, because saying that you add noise to parameters and this breaks everything is the same as saying that the minimum is brittle. So the basic idea of the proof is again the following. The first step is to note that parity requires layer norm blowup to overcome the problem with close outputs. The second step is to say that all sensitive functions require layer norm blowup. And the third step is to understand that layer norm blowup causes sharp minimum. Any questions about the idea? No. Okay. Then time to formalize this. And to formalize this, let's understand, let's just define the blowup. So we have this multiplicator value for each token and for each transformer layer. So this value of n is just something that is multiplied on hidden representations in each layer for each token. And we aggregate it, we take the maximum of that over all tokens and the product of that over all layers. And then we say that this value is the blowup, and the higher is the blowup, the more the representations get inflated somewhere in the computations of transformer. And then we can formulate the property related to this value of blowup, which is the first main theoretical result of the paper. So the first theorem states that with high probability over the choice of input bit string, we can say that average sensitivity of a function represented by transformer is bounded from above from layer norm blowup in this transformer. But not only the layer norm blowup, but also blowup multiplied with some constant c, and this constant is tied to the parameter norm of the transformer. So the higher is parameter norm, the higher is c. And basically this says that there is a trade-off between the parameter norm in the transformer and between the layer norm blowup inside its computation, if the transformer represents a sensitive function. So if transformer represents parity, then either its blowup is high or its parameter norm is high. But the important thing is that there is non-trivial prediction only for functions with average sensitivity, which is higher than square root of n log n, because otherwise the right-hand side just becomes zero. Because, for example, for majority function which has sensitivity square root of n, the right hand, like this denominator in the right-hand side is zero, and so yeah, and so the right-hand side becomes zero, and you don't have any meaningful prediction. But for parity, the sensitivity is n, and because of that, the right-hand side grows with increase of n, and the left-hand side must also grow. So if you train transformer for parity with increasing inputs, with increasing input length, the resultant transformers will either have higher parameter norms again or higher layer norm blowups. And that was basically the first step. So this theorem corresponds to the step about saying that all sensitive functions require layer norm blowup. It doesn't say anything about lost landscapes yet, but here we draw a connection between sensitivity of a function and layer norm blowup. And in practice, you can really spot that this happens. So this is the plot for result of experiments where we trained different models or like different small transformers for parities of different input lengths, which is the same as just the functions of different sensitivity. And you can spot that the parameter norm slash layer norm blow up trade-off really exists. So if you have a model with low parameter norm, say 10, then the layer norm blow up will inevitably be high, and vice versa. If the layer norm blow up is low, then the parameter norm must be high. And also, another important observation is that if you fix parameter norm of the model, let's say that we fix a model with parameter norm 20, and we want this model to represent parity of length 5 or length 20, then for length 5, layer norm blow-up will be lower, something like 10, and for length 20 or 25, layer norm blow-up will inevitably be higher. So yeah, for if you increase the sensitivity of the function, then this trade-off becomes harsher, which is essentially what the theorem says. Any questions so far? No? Okay, cool. Then the second step is to link the layer norm blowup to the loss landscape sharpness. And for that, we need to define sharpness first. And we introduce the value of average direction sharpness, which is some kind of sensitivity, but not for inputs, but for parameters. So we have this transformer T, which has the parameter theta, and we add to theta the random noise delta. And then the average direction sharpness would be the average change in the output of the transformer over all possible inputs and all possible noises. So you can just think of this value as of approximation of Hessian norm in the minima. The higher is the average direction sharpness, the more brittle is the minima, and the more brittle is the loss landscape. And then we can use this value to formulate the second main result. So it states that in the limit, average direction sharpness is bounded from below as the sensitivity of the function over n. So what this means that if you have a sensitive function, and not just sensitive, but with sensitivity, with average sensitivity on the order of n, then the right-hand side in the limit will become constant because this it will become constant, and so the average direction sharpness of the parameters of our transformer that represents this function will be bounded from below, so it will be divided from 0, which basically means that the loss landscape for this function, also for this transformer, will be sharp. And this is the second and last step. This is the step where we say that layer norm blowup causes sharp minimum, because yeah, this happens. Yeah, because here we linked the layer norm blowup that we introduced before for sensitive functions to the increased average direction sharpness. And so the main takeaway from this theorem is to note that tiny perturbations in the parameters lead to substantial change in predictions on the inputs, which is the definition of average direction sharpness. And this means that sensitivity in input space, this average direction sharpness on the order of n, entails sensitivity in parameter space, which means, average sensitivity on the order of n entails sensitivity in parameter space, which is increased average direction sharpness. And yeah, this statement in bold is basically the TLDR of the paper and the main takeaway. In practice, this also can be spotted. So if we have two functions, parity and majority, and we train transformers for those functions for different sequence lengths and measure the sharpness, we can simply note that for majority, the sharpness increases, but mildly, and it always stays low. And for parity, the sharpness is always higher. And also for parity, the sharpness of the sharpness of the function, of the minima increases with increase of the sequence length. And so it increases and increases, and then at some point you just can't train transformer for this function anymore. And the hypothesis is that the minima just became so sharp that with your current hyperparameters, your optimizer can't find the minima of this sharpness. And at this point, we can come to the implications of the theoretical results. So again, do you have any questions about the theorems that were stated before? Everything is fine? Okay, everything is fine, yes. Then what about implications? So first one is that randomly initialized transformers are insensitive. Why this happens? Because we like here and further will base all the implications of the second main result. And from it, you can conclude that with high probability, its random noise to a sensitive transformer breaks its sensitivity. So you cannot derive this strictly from this formula above, but this can be derived from one of the steps during the proof. Here you can just see that if you add random noise to the sensitive transformer, it will start outputting something very different. This is because of this non-zero sharpness. But actually, it will not just output something different, it will completely break its sensitivity. So if you have a sensitive transformer and you add random noise to it, it will become insensitive. And this means that sensitive transformers are isolated in parameter space because you make any step in any direction, and then with high probability, the transformer is not sensitive anymore, which means that there are just much more transformers which are insensitive than the transformers which are sensitive. So this entails that transformer with random parameters is very likely to be insensitive. Which is, again, a known empirical observation from prior work. And now we have an explanation for this. So this picture is from the paper about simplicity bias by Satwik Bhattacharya. And here, the authors found out that if you randomly initialize a transformer, then the models that they get are clustered around some very low sensitivity, while LSTMs have much higher sensitivity on average if, again, they're randomly initialized. And this is, again, one of the empirical observations about simplicity bias. And here we say that, okay, this makes sense because drawing an insensitive transformer from all possible transformers is just much more probable. Another implication is that length generalization is hard. And why is that? That is because for a sufficiently large n, we have non-zero and high average direction sharpness. And this means that if you have a transformer which represents some sensitive function, but it doesn't have exact correct parameters, so it deviates from the minima a little bit, then there exists such n, starting from which it will start giving different outputs. So there exists such n, starting from which it will have non-zero error. That's because the average direction sharpness is that's because in the limit, the average direction sharpness is non-zero. So this means that an average direction sharpness is here with the scale of the noise approaching zero. So this means that for some n, there will be, so for any row, for any scale of the noise, even very little, there will be n starting from which the sharpness will become large, and so there will be n starting from which any deviation from the exact minima will bring you difference in the outputs of the transformer. And so to achieve perfect length generalization, the transformer must be exactly in the precise minimum of parameters, which is, of course, infeasible in practice. And so the takeaway here is that if you want a transformer which represents a sensitive function and length generalizes for the sensitive function, it has to be in this exact minimum of parameters, which is hard to find in practice. Another takeaway is that optimizer finds the least sensitive solutions, which is also an empirical observation known from before. And here's why. So according to the theoretical result, the less sensitive functions have flatter minima because the sensitivity is lower, so the average direction sharpness and the sharpness of the minima is also lower. But the deep learning optimizers now work this way that if several different functions both have, if all of them have the same zero error on the train set, so they all describe the train set, but they have different sensitivity, then they have minima that are more or less sharp, and the optimizers converge to the flattest minima that they can find mostly, and so the optimizer, if it can pick out of different different functions, will converge to the function with the flattest minima. And the function with the flattest minima is coincidentally also the function with the least sensitivity. And that's why optimizer, if it has some freedom, will pick the function with the least sensitivity, which is the origins, again, of this low sensitivity bias in transformers. And in practice, how we can find it? We can do the following experiment. So here we have a random function from bit strings of length 10 to 0 or 1. And we train transformer on this function, but we give it not the whole in the training set. We give it not all possible bit strings of length 10, but we give it some random training set of 100, 200, or 500 samples, which corresponds to different clusters here. And so if transformer doesn't see the whole possible space of all bit strings, then of course it won't converge to the initial random function that we have, but it will converge to something. And we are interested in the properties of the function to which it will converge. So we give a transform. So yeah, during training, we presented to the transformer this 128 samples. It achieves zero error on them and predicts something for the other samples which were not in the train set. And then for all the samples, we can compute sensitivity and sharpness. And we see that for the case in the cases where the train size was smaller, the sensitivity of the resulting function was lower. That's because the transformer had more freedom. It had more functions to choose from when converging, and it chose the function with the flattest minima because the sharpness is also lowest for the screen cluster. So it chose the function with the flattest minima, and that was the least sensitive function. So it was known that transformer picks the function with the lowest sensitivity, but here we also can prove that it does this because the function with the lowest sensitivity has the flattest minimum. And when you take the freedom of transformer from it, it starts picking the functions of higher and higher sensitivity because only they can explain the train set and the sharpness of the solutions increase. And then the last implication is that the Scratchpad makes training easier. And you can also easily understand why this happens, because if we again return to the example of parity, then the sensitivity of parity is proportional to n. But you can construct a Scratchpad for parity in such a way that the sensitivity of each individual step will be constant. So you can construct a Scratchpad with n intermediate steps for parity, and the sensitivity of each step will be just constant and not proportional to n. And then when transformer will be learning each individual step, the sharpness of lost landscape will not bound from below. So they will not have any problems with brittle minimas. And because of this, transformers will not have face problems when trying to learn the functions. So Scratchpad, even in the cases when the model can theoretically express a function without a Scratchpad, adding a Scratchpad can still help, because the lost landscape will just become better and easier to learn for the transformer. Yeah, and this is it. So here's the summary, and yes, we are ready to answer the questions.